So I hope you can all hear me. Like Trine introduced, we work a lot with materials compatibility in hydrogen environments. And my focus today is to dive a little deeper into the embrittlement mechanisms, dissociation, hydrogen permeation, what happens when hydrogen enters steel. And then a lot of the questions we get is on hydrogen compatibility, what sort of tests to perform, and a general evaluation. And just a quick intro, why is hydrogen even a problem? Well, this is a fracture in a bolt, but the general characteristics of hydrogen failures is they are rapid. You don't have a warning like a fatigue crack growing over time. Here you see a very, very small initiation site and then a final fracture. So we really have to watch out for these. This is just to show, we see a lot of studies illustrating the embrittling effects of hydrogen. Here you have a tensile test specimen in air compared to one in hydrogen. And normally for steel, you would have necking and some ductility, as you see in the left image. And in the right image, you have full embrittlement from hydrogen. So this is, and parallel cracking to the fracture surface. This is a study showing the embrittling effect. And our purpose generally is to evaluate, well, when does this occur? Do we have a stress level relevant for this kind of damage? Because hydrogen does not always cause damage. So where are the limits? This is our key points for our work. And hydrogen diffuses in the metal lattice. So it can also be a delayed fracture with hydrogen diffusing into strained areas if you have yielding somewhere in your system. So it is a species. Something else we have to emphasize is that hydrogen is not new. For instance, we had hydrogen in town gas in Copenhagen up to 50%, but there you had the possibility of selecting materials with high ductility, even rubber tubes, pressures were low. So with the demands for today, we have to consider using materials that are generally maybe considered not suitable for hydrogen service, but then perhaps design the application to suit it, to be able to meet demands for high pressure, temperature, corrosion process. Of course, cost of power to X is in a central issue. But how does hydrogen enter the material? Well, here I have a notched specimen I made with the hydrogen crack, and you have schematics above it with a crack tip. And we have several hydrogen mechanisms. They're quite academic. We don't need to understand everything in detail for us to be able to assess the risks. But generally, hydrogen enters the steel and then diffuses due to gradients. And it could be a gradient of temperature, pressure, strained areas, concentration gradients. It could be a gradient on different size of a pipeline wall. And the source of hydrogen, we often get the question because our perspective is failure analysis. So did the hydrogen come from manufacturing or was it from service? So from manufacturing, you could have hydrogen sources from steel making, welding. From service, it could be due to corrosion processes, cathodic protection, overprotection, and related to power to X for hydrogen transport and electrolysis. So we have many sources, and in generally, the mechanisms are the same. When we talk about metals, we look at phase diagrams like the ones I show here. Here you have temperature and absorbed hydrogen. And hydrogen can be considered an alloying element. And in generally, when we do alloys or make alloys, we do it at high temperatures and add some different elements. The thing about hydrogen is that you can have alloying at the sub-0 degrees and upwards. So it's quite tricky. And if you have hydrogen atoms present on the metal surface, they can be absorbed into the metal. Normally, steel would contain different phases in the microstructure, like ferrite, austenite, martensite even, and they have different solubility and diffusion properties, and also sensibility to hydrogen. For example, martensite is unwanted for hydrogen fractures. You may also have hydrogen forming at the surface due to corrosion. And just to introduce hydrogen as an atom, it is the smallest atom, and it's the only one without neutrons in the core, and it's really a building stone for many other things. And it may be present in metals as a solute atom, so interstitially. In the lattice, we have, most of you may know that most metals consist of a metal lattice. It can be as intermediate phase like hydrides. We often see this in titanium. This is also unwanted, and it can actually recombine to H2 inside the material and cause small explosions. So there's different mechanisms. In general, we have this is just a schematic showing a crack tip and grain boundaries, and you would have hydrogen collecting in places where it can cause the most damage. So it could be at the grain boundaries if you have dislocations in the metal, or areas of three axial stresses, like we have here in a plastic zone in front of the crack tip. And there you have the metal lattice distorted by mechanical straining. This is also an area for hydrogen to collect. Then if you have the crack evolving, you may actually have hydrogen escaping from the crack due to new surfaces formed. This could also be hydrogen from manufacturing processes escaping and causing damage elsewhere. We would normally characterize this as internal hydrogen embrittlement, IHE. And then the cracking can, of course, continue to propagate. I won't go into very detailed explanations of these, but we do have different mechanisms of hydrogen embrittlement. This one is HELP, hydrogen enhanced localized plasticity. Here again, we have an illustration of the plastic zone in front of the crack tip and voids forming. Another mechanism is hydrogen enhanced decohesion mechanism, where you have decohesion forces acting in the metal lattice. So sort of dilation of the lattice causing damage also. Then you have adsorption induced dislocation emission. So rather than decohesion, it's actually adsorption at the interatomic bonds of the metal lattice. Generally, this is quite an academic approach. A lot of simulation work is ongoing and studies, and for our purpose to assess the risk and define the limits, it's not necessary to understand everything to the very bottom. We just need to assess and explain when and in which form hydrogen damage occur. And also a very important point, hydrogen in itself does not cause damage. And as we can see in the Venn diagram on the next page, we need to have a combination of environment, mechanical loading, and a susceptible material. So if you have sufficient amounts of hydrogen in a susceptible microstructure and mechanical stresses, then you may have damage. So if you have a very susceptible material, it may take less mechanical loading or a less severe environment to cause damage. Otherwise, if you have extreme hydrogen charging, then a less loaded specimen or component may actually be damaged. But will hydrogen actually enter the steel? This is also a question we get quite often, because if you take dry hydrogen gas, it's molecular, H2. And as I just tried to explain, we have atoms entering the metal lattice. So what happens? Well, we have dissociation at the surface. And again, there's a lot of work is ongoing in this area, but some of the driving forces for H2 to become atomic hydrogen is partial pressure, chemistry, available species at the surface, because hydrogen has high affinity for recombination due to the electron cloud with just one electron, like I tried to show. And the degree of dissociation depends on how much hydrogen is available. So if we have very high pressure, 100% hydrogen, you may have more dissociation at the surface than at lower pressures. Then we have species promoting uptake. This could be hydrogen sulfide, sour gas. If you have palladium, noble metals like gold would not recombine with hydrogen, so they have no affinity for recombination. On the schematics, you coming up. We have an oxide layer. We have an oxide layer trying to expel the hydrogen atoms. I'll get into that. Once the hydrogen atom is free to move inside the atom, it will diffuse due to gradients, like I just tried to explain. This is just a quick visualization of a tube hydrogenated by Ney's test solution, where we have a lot of hydrogen going into the steel. But even just after 24 hours in this glycerin test cup, we have a significant amount of hydrogen bubbles forming. They are collected. So yes, this is just an example of, yeah, it does diffuse through the steel. Discussions are ongoing on which species we can add or remove from the gas to promote or inhibit hydrogen embrittlement. So as I mentioned, we have the hydrogen sulfide to the right. Here we have the baseline of one as just pure hydrogen gas. You have hydrogen sulfide promoting the uptake significantly. Then you have water content, also maybe a factor in promoting the uptake. Carbon monoxide, like we had in the town gas, would inhibit to some degree, and oxygen maybe even more. And there's discussions ongoing on whether or not to add oxygen to remove the effect of hydrogen embrittlement. The inhibiting effect on oxygen in a dynamic system really depends on the crack growth rates, the R ratio, and well, what happens? The pre-adsorbed oxygen, it actually raises the activation energy. So here we have an illustration of the metal lattice. If the red dots, they're oxygen, they already took up the spaces and outcompeted hydrogen. So if oxygen is present, it's more difficult for hydrogen to diffuse into the lattice and actually dissociate at the surface. So it does have an effect. It raises the activation energy for hydrogen dissociation. Like you can see on the two curves, you have a higher peak here, higher activation energy. So it's more difficult for hydrogen to diffuse into the metal. However, there's more parameters to consider. If we take hydrogen and oxygen, and especially in electrolysis, it is very much a risk of evolving a detonating gas. So safety is a key issue. Another aspect is, well, at the design stresses, does it actually have an effect? Here to the right, we have a crack growth test where we have a steep curve, that is crack growth in oxygen. Then we have addition of, in hydrogen. Then we have addition of increasing oxygen levels, and we can see how the curve flattens, and really crack growth is almost inhibited. At the end, the curve becomes steep again, and that is where oxygen is removed. So that definitely shows the effect. However, to the left, we can see that at a lower stress intensity factor range, delta K, we actually see pretty much the same crack growth rates as in air, even though we have oxygen addition. And many systems are designed to be at delta Ks below 10. So oxygen additions may not have an actual effect. Then there's the thing about the R ratio that also has an impact. So it really does depends on many factors, and it is not just an easy yes or no question. We also have requests on humidity levels and the effect of humidity, especially our metrology department works with that. That is also a focus area for us to consider. And speaking of water, we have electrochemical charging, because once hydrogen enters the steel, the source of hydrogen, it really doesn't matter because the fracture mechanisms are the same. We've worked a lot with this. This is just a presentation of another study where they compared the 1980s pipeline steel with the new best practice steel. We have steel B, which is the new one, with very small grain size, little defects, and permeation testing was performed in this cell. It's a standardized Stefanathan cell that we also work with, where you have an electrolyte to measure the diffusion coefficient. And what they found was that, well, you have a much higher diffusion in the new pipeline steel, maybe because you don't have as many traps for hydrogen, because if you have a steel with many impurities, weld defects, or many places for hydrogen to hide and collect, then yes, then it may stay inside the metal and cause damage. So it is, of course, a measure of that. Focus here is on pipeline steels, but we are trying to define the weak spots. So very much focus on welds is our way forward. There is also the question of whether electrochemical charging is too conservative, because you get much more hydrogen into the steel compared to in a gas. These are some other studies. We've worked a lot with electrochemistry, we still do, cathodic protection. This is just a curve we've done a few years back, where we had the delta K at 25, so quite high. We have cathodic protection levels in the center. You have the potential here, and you have a crack growth rate. If we move to the left, you'll have corrosion. Of course, that is the whole point of adding CP, cathodic protection. It is to avoid corrosion. But if you increase or decrease the cathodic potential, you actually have hydrogen evolution. And we've seen a lot of damages from overprotection by cathodic protection, because you have so much hydrogen forming that it enters the steel. If it is an offshore construction at the seabed, there might be sulfate reducing bacteria, hydrogen sulfide, which increases the hydrogen uptake even more. And at the seabed, you may have oxygen-free or anaerobic conditions, which is also a bad thing. So again, hydrogen can enter in many ways, but the fracture mechanisms are the same. This is just a quick illustration of the same, mainly just to show that at certain cathodic protection levels, you may actually have deposits forming inside the crack, inhibiting crack growth at a certain point, but still, in the end, it may just continue as a fatigue crack. What we've done recently is trying to define the hydrogen sensitivity ratio. This was, we've done this multiple times, but this was a study of high strength bolts, because it is a continuous discussion of the effect of thread manufacturing. When you roll a thread, you get a deformed zone with a high hardness. And what effect does that have? High hardness is not good when it comes to hydrogen embrittlement, but there are more aspects to this. Hydrogen is not easy. So I polarized the specimens to minus 1200 millivolts. This is considered overprotection, so trying to get as much hydrogen into the specimens as possible. I just see water as electrolyte, and then it was a static stepwise loading, so increasing the load in steps. This is just quickly to show that a comparison between rolled and cut threads showed hardnesses of a surface hardness above 400 in the rolled deformed zone in the thread root, and the cut thread a bit lower, but still very high. It was 10.9 volts, so about 360, 370 vigors, much higher than allowable hardnesses in pipeline steels or welds or related issues. The hydrogen sensitivity ratio was calculated. We had a load cell applied, and the general view was that they were not very hydrogen sensitive, actually. The roll thread were actually a bit less sensitive. And examining the specimens, I found that here we have a cross section of a thread showing cracking in the surface layer. The white area is the deformed, the very hard layer, and we actually have crack blunting once the cracking reaches this laminar structure formed by the rolling process. So it is not black and white. We can have high hardness, but if you have a laminar effect like this, it may actually inhibit crack growth to some extent. This is just some scanning electron images showing that cracking is primarily limited to the surface. Yes, and even plastic deformation occurred in some samples. So this is another aspect of hydrogen embrittlement testing. And what we would like to achieve, here I have to the right a relation performed here at Force Technology a few years back, which was a relation where we have pH and electrochemical potential, and then the relation between partial pressure of hydrogen related to these parameters. And this was to avoid testing in hydrogen sulfide, because we've done a lot for the oil and gas industry, and hydrogen sulfide is poisonous. So in relation to Power-to-X technologies, we would like to achieve a similar relation to be able to test at much higher pressures than possible in our labs, 1,000 bars or even higher. We still have the same charging into the sample. So this is something we would like to continue working with. Yes, I know it's very long, but is the material safe for hydrogen service? That is a very hot topic, and we have different methods because actually most materials are sensitive to hydrogen embrittlement. We have different, of course, the standard saying something. Then NASA worked with hydrogen embrittlement for many, many years, and it's quite well founded in academics what they did. The message is maybe not the best because most materials are sensitive. And actually, it can be over-conservative just to use compatible materials, because as we see from here, we have the green materials with little hydrogen embrittlement sensitivity. These are typical pipeline steels. But if we take IC 4140, it is extremely embrittled by hydrogen. It is the red one. But this is a material used for high pressure hydrogen containers. And how is that even possible? Well, this is another aspect that we're working with. You have to consider the material for the purpose. So here it is a small object. It's easy to control defects. It's very easy to continuously check it by NDT methods. And you also have the option of engineered defects. So they could add a notch and make sure that we will have leak before break or burst or something catastrophic in an object like this. So these are also tools to work with when designing a component. And it's really just to emphasize that you can't just look in a table and say, yeah, this material is safe. Of course, that's a good thing, but there may be gray zones where we can work with materials and make it work anyway. Another option is there's an ISO TR 15916. Generally the same approach, focus on, are they embrittled? Yes, no. If we dive into it and look at different alloys, carbon steels, low alloy steels, the general picture is that very few materials are considered suitable. Some are not suitable, but for most of them, they get an E in the column I marked by blue, saying we need to evaluate this. And that is what we work with. And how do we evaluate? Well, we would like to use testing as an enabler, because you can look, there's many studies performed, but it's really the best way. Just a quick example for the ASME B3112, it was changed based on testing. We had for example, the X70 getting a different rating, being able to use it at higher pressures due to a significant test program. But you have really extensive test demands in that standard. And maybe it's a good idea to consider other approaches. Here to the right, I have a diagram. It's made where you have the floor size, which is the stress. And first you will reach the limit of fatigue. Then you have a static stress corrosion fracture threshold. And at the end, you'll have overload fracture out to the right. So working with these parameters and fitting your material and your stress level when designing and doing it in a smart way and taking the same approach when testing is a topic to consider. So focus on engineering critical assessment and evaluate the critical defect size could show to be a good approach. And this is just all the examples of how easy it is to make tests to show how hydrogen embrittles. But like I've marked with the blue circles, these are pretty much the levels where you would have normal pipeline steels, the stress levels. So looking closely, maybe you can be safe even with a steel that is embrittled at certain stress levels or certain delta Ks. And to focus on how we have done full-scale testing, I have a case example. The first one is in a X65 pipeline, spiral welded. It was for oil and gas purposes, so it was charged by NACE solution. And on the outside, we have a patch probe we developed, which can sense the hydrogen. And we have the readings. So for the first day, no hydrogen really diffused through the surface. Then after 1 day, we have the curve increasing to a certain level, and then you pretty much have steady state diffusion through the pipe wall. These were situated on the outside. Just a simple visualization on tape on the outside. You have hydrogen blisters forming due to diffusion. So you don't always need very high-tech equipment to make sure or to visualize that that hydrogen is actually present or coming out of the pipe. On the inside, during the test, blistering in the metal surface developed along welds. This is a microsection through a blister. And as it was, the reason why this was inspected was that weld repair had occurred. And this is really a focus area, because when you weld, if you grind, you have the risk of forming very hydrogen sensitive faces. And this was the case here. We have cracking along the entire weld. To the right, you see a cross section with cracking. And here there's another section with displaying hardnesses up to about 300 Vickers. And for this test solution, where you have really high hydrogen diffusion, that is enough to cause cracking. So this is an example of a full-scale test. This may not have been showed in a tensile test. Yes. To go back to the engineering critical assessment of defects, we had another full-scale test where it was a pipeline steel. Cracks or defects were discovered. There's a weld toe crack, as you can see to the left in the schematics. You have the anticipated crack path, and to the right there's a cross section showing this this actual defect with the weld metal to the left. And this is also a question we get: if defects are observed, well, are they dangerous? Is something going to happen? So this was tested at this stage, mainly to consider, well, are we going to have leakage, unstable fracture? Is cracks going to grow from this defect? And will it, well, if not, then is it going to reach a critical size within the lifetime? Because you can allow cracks to a certain level, but if they get big enough, they will start to grow. For example, like a fatigue crack. So a CTOD testing, compact tension opening displacement for the fractures to assess the unstable fracture aspect was performed. Then we did a full-scale test with high stresses on a pipe section with the largest defect observed, and then fatigue testing. And the full-scale test was a stepwise pressurization to failure or general yielding. And what was found, you can see the plot to the right, a crack growth regime with a function of stress ratio and delta K was established. But actually defects at 1.5 millimeters or below did not cause cracks to grow. So the steel proved to have a very high flow tolerance. And even though 1.5% permanent deformation was measured, no crack growth was measured. This was tested by acoustic emission. So this just proves to show that it might be a good approach. Because what about the rest of the pipelines? Could we even use those? My last case example is a field test of hydrogen natural gas grid. We did it with Danish Gas Technological Center. Main points are that, well, it was X70, which is most of the Danish gas grid, and had 100% hydrogen gas. And as you can see to the right, it was a pipeline with a weld, which is considered the weakest section. And we filled it with concrete to ensure that we had a lower volume. This is something we work quite a lot with in our labs. How can we limit the risk by decreasing volumes of hydrogen because the safety aspect is very important in this case. And conclusions were that there was no crack growth observed after full-scale dynamic testing. This is the test setup, and it was run at plus minus 15 bars with a test pressure of 70. After testing, of course, there was NDT performed ultrasonic testing at magnetic particle, MPI, and then metallographic to further confirm. This is also something we quite often do, because you may have signals from the NDT methods, but just to confirm what the signal actually is. And like the assessment of the defect, we looked around the wells, because this is where you would normally have cracks developing. And as you can see from the sections, nothing was observed. So this was a good thing. And the general evaluation was that maybe we don't see a problem in putting hydrogen into the gas grid. So our main target here for signals is, of course, to look at where do we see risks of damage and defects developing, and focuses on stresses, the material, and of course the environment. And we see wells as a focus point for our work. And I know it was a very long presentation, so just to sum up, yes, hydrogen does enter the steel to some degree, but it doesn't necessarily cause damage, and we need qualified evaluations to consider this. And we have different parameters affecting hydrogen diffusion, dissociation at the surface. We may work with species inhibiting this, but again, it is not a simple yes/no question. The same goes for the hydrogen compatibility of materials. You need to evaluate the whole design. You can't just say if a material is suitable. Well, for very few materials, this is true. And the possibility of electrolytic charging is something we work with. And from our case examples and general experience, we really recommend to assess the entire, what happened? Damage scenario. My computer just froze. There is. Okay. It's tired now. Yes, it's too hot. Force a test focus for future, because as Trine mentioned, this is a 4-year project going on, and we have many other activities within hydrogen and Power-to-X. We focus from here on our fracture mechanics testing in environments and gas mixtures, hydrogen, and we perform full-scale function and component testing. And then we really think that permeation testing is very important, and my colleague Johan will get into this. And we also work with other relevant tests for electrolysis and Power-to-X technologies, ammonia. And we look forward to presenting many more results to you once we're a bit further in this project. So thank you so much. I had a video. I'm not sure if the computer is tired. From the full-scale test that we did perform. Otherwise, you'll get the link. Yeah, we'll send you the link to the video. Thank you so much.